Alright, chemistry students, welcome back. So, in my last video, we talked about the concept of the mole, and we talked about the problem that we have with chemical equations. And that problem, just to rephrase, was that if we have a balanced chemical equation like this that's telling us to combine a certain number of molecules of a substance, we can't actually measure out that many molecules. For example, this statement is telling us to measure out 2 molecules of sodium chloride and combine them with 1 molecule of barium nitrate to produce 2 molecules of sodium nitrate and 1 molecule of barium chloride. We can't measure out 2 molecules. We can't pick them up with little tiny tweezers. So, how do we go about solving the problem? Well, what we determined at the end of the last video was that these numbers in the chemical equation aren't necessarily the number of molecules, but what they describe is the ratio between each of the elements or each of the molecules in this chemical equation. So the ratio of sodium chloride to barium nitrate molecules is 2 to 1. We'll always have twice as many sodium chloride molecules as barium nitrate molecules. And because of that, it doesn't really matter if we have exactly 2 molecules and exactly 1 molecule, so long as we have twice as many of this as this. A way to think of it is to pictorially represent this chemical equation using these bags. And we'll call this symbol a bag that holds exactly the same number of molecules as another bag. So this bag is capable of holding exactly the same number of molecules as this bag, is capable of holding the exact same number of molecules as this bag. Each of these bags holds the same number of molecules. And for now, let's assume that it doesn't matter how many molecules are in the bag. So we can represent this pictorially by saying that if we take 2 bags of NaCl that contain the same number of molecules, and we combine them with 1 bag of barium nitrate that contains the same number of molecules as these bags, then what we'll create is 2 bags of sodium nitrate and 1 bag of barium chloride. Simple enough. Well, let's say, to make this even simpler, let's say that a bag contains 10 molecules. Well, that would mean that we would combine 20 molecules of sodium chloride with 10 molecules of barium nitrate. Again, that ratio remains 2 to 1. And we would create 20 molecules of sodium nitrate. Each one of these bags would hold 10, and 10 molecules of barium chloride. Again, this would be in the ratio of 2 to 1. We could do that with 100 molecules or 1,000 molecules, and the result would end up the same. As long as these bags hold the same amount, the equation will still hold true. So the big question, and the thing that leads us to the mole, is how many molecules is it practical to put in the bag if we're going to do chemistry with these bags of molecules? And here's where the problem comes in, and it was a problem that wasn't able to be solved for a good long time. The issue, as we've already determined, is you can't count the molecules. You can't just pick out a molecule and count them and put them in the bag, because picking up molecules is nigh impossible. They're so small, and doing it is not only almost impossible, but also completely impractical. It would take you forever to count out a reasonable number of molecules to get any kind of reaction. So we can't fill up these bags by counting them. We can't just say, oh, well, we have exactly 10 here and exactly 10 here, a small reasonable number to count. It's impossible. And the other issue we have is where we're like, oh, well, I got it. Well, how about, rather than having the bags have the same number of molecules since we can't count them, how about we just make them the same mass? We'll just say this bag is 10 grams and this bag is 10 grams, and all the bags are 10 grams, and that'll work out just fine, right? Well, unfortunately, that doesn't work out. Because, as we know, some molecules are heavier than others. Barium nitrate has 1 molecule of barium nitrate has a completely different atomic mass than 1 molecule of sodium chloride. It would be like if one of these bags was filled with feathers, and one of these bags was filled with bricks. Barium nitrate is much heavier. And we weighed out 10 pounds in each bag. Well, obviously this bag is going to contain way more feathers than this bag contains bricks if they both weigh 10 pounds, because 1 brick weighs a lot more. So that doesn't work either. If we weigh out the same mass of each of these substances, even if we weigh out twice as much mass as this substance, we're not going to have everything in the right proportions. We're not going to have this 2 to 1 ratio. So the bags can't be the same mass because some of the molecules that go into the bags are heavier than others. They have different weights. So what's the solution? Well, here's what a convenient solution would be. And wouldn't it be awesome if this were the case? So we make the assumption that each bag contains the same number of molecules because it needs to. And then we say that the mass of the number of molecules that goes into the bag will be equal to the atomic mass of whatever molecule is being put into the bag. See, that would be interesting, because then we would weigh out a certain amount of sodium chloride that would be proportional to its atomic mass, and we would weigh out a certain amount of barium nitrate, which would be proportional to its atomic mass. So we would weigh out more mass of barium nitrate to fill up this bag than we would to fill up this bag. But when we were done, the convenient thing would be that after we completed that, these bags would contain the same number of molecules. Now, wouldn't it be convenient if we had a number like that? A number of molecules that made that work. And we do. It seems like it would be crazy for that to work, but individual molecules are so small that if we're putting one molecule into the bag at a time, we eventually reach a point where a certain number of molecules is exactly the weight in grams that's equal to the atomic mass of whatever we're weighing. And that amount of molecules is called the mole. So let's work on this practically so that you can work with this a little bit better. So this number does exist. Even though it seems like an overly convenient solution, this number does exist, and it was founded by a scientist named Avogadro a very long time ago. And he found this number, and this number is a mole, which is 6.02 times 10 to the 23rd objects, or things. We use a mole in the same way that we use a dozen. A mole is this number of things. 1 dozen is 12 things. This number is used in practicality for things like numbers of eggs or numbers of donuts. This number is used practically for numbers of atoms, because as we've seen, weighing out or determining the same number of atoms is not a trivial task, and this number allows us to do it pretty easily. And the way that it works is that we say that a mole of any atom or any molecule means that we have exactly 6.02 times 10 to the 23rd atoms or molecules. And then the super convenient part about this is that the mass of 1 mole of any atom or molecule is exactly equal to the atomic mass of that atom or molecule in grams. So, how do we work this practically in the lab? Well, we know that a mole of sodium chloride is this many molecules, and that the atomic mass of sodium chloride is 58.5 AMU. We get that amount from the periodic table. Sodium weighs approximately 23. Chlorine, I'll try to squeeze this in here, weighs approximately 35.5. So the atomic mass of 1 molecule of sodium chloride is 23 plus 35.5, or 58.5 AMU. So because moles are so convenient for this, and we know that the mass of a mole of atoms or molecules is equal to the atomic mass of that atom or molecule in grams, that means that the atomic mass of 1 sodium chloride is 58.5 AMU, but the mass of a mole of molecules is exactly 58.5 grams. So we can go to the scale, we can measure out 58.5 grams of sodium chloride, and that will contain exactly this many molecules. Now that's getting us somewhere, because then if we need to combine that with barium nitrate, well, all we need to do is add up the atomic mass of barium nitrate, weigh out that amount on the scale, and then those two quantities contain the exact same amount of molecules. And since they're exactly the same amount of molecules, it's like putting them back in these bags that contain the same number of molecules. And then all we need is 2 bags of sodium chloride, or 2 moles of sodium chloride, combined with 1 mole of barium nitrate, will create 2 moles of sodium nitrate and 1 mole of barium chloride. Now, if you're having trouble visualizing that, just rephrase your thinking in terms of dozens. It'd be very easy to say that, well, 2 dozen sodium chlorides plus 1 dozen barium nitrate would produce 2 dozen sodium nitrates and 1 dozen barium chloride. So we can think of a dozen as 12, and that's fine. A mole is the same, it's just a much larger number of things. And the reason we have to use this very large number is because we can directly relate that number of molecules to the atomic mass of whatever molecule that we're weighing. Put it on a scale and make it work. So very, very quickly, let's do this. If we go and we get a scale, we'll put a plate on that scale, and we zero it, and we take sodium chloride, and we dump sodium chloride onto here to the tune of 58.5 grams. Slow it down. Gonna slow down a little bit here. Just a touch more. Oh, we went 58.6. We took maybe just a little bit of that off. 58.6. 58.5. Exactly 58.5 grams of sodium chloride. In this plate right now, there are exactly 6.02 times 10 to the 23rd sodium chloride molecules. And we can tell that because we already know sodium chloride's atomic mass. So this solves our problem. This gives us an equal amount of molecules that we can use when doing chemical equations so that we know exactly what to do and exactly how many molecules we're combining into the chemical equation. And we can precisely quantify the number of molecules going into the chemical equation. We know the number of molecules in that pile. And that, my friends, is crazy awesome. All right. I hope you found that as interesting as I do. I love this stuff. We'll talk more about it on Thursday. I'll post another video for you tomorrow. Take care. Have a good day.